Hi, it's Miss Lenorvitz, and if you've made it this far, congratulations. It means you've finished part one of When Did They Die, and you're ready to endeavor into part two. So this short video is going to take you through what you need to think about in part two. So in part two, you're going to be revisiting the graph that you created in part one and the data table from part one in order to analyze the remains of these 6 different individuals. So remember, the remains are their leftover bones that have been discovered deep buried in sediment. And from those sediments, you have sampled the atoms that are present there, and you've tested them for the number of unstable Lake Champlainium atoms remaining and the number of stable Colchesterium atoms that are remaining. Your next step is you're going to need to put these names of the remains in order. You're going to be using relative age dating here, so you want to think back to what you know about. So you're going to be filling in first this first column right here. Notice that you want to organize them so that the youngest sample is listed at the top and that the samples get progressively older as you go down the list. Let's take a look at why you need to do that and what you need to think about here. So remember that over time, unstable radioactive atoms, also known as parent isotopes, are going through radioactive decay to become stable non-radioactive daughter isotopes. So that's part of what you need to think about here. The longer this process has been going on, the more time there's been that parent isotopes are decaying into daughter isotopes. So you can think about the fact that older samples are going to have more daughter isotopes and fewer parent isotopes, and younger samples are going to have more parent isotopes and fewer daughter isotopes. The other aspect that you need to think about here is relative age dating. So you'll recall back, think about the law of superposition. This tells us that newer layers form on top of older layers. Remember, that law is based on the observation of current processes on Earth, that when streams carry sediment downstream to the mouth of the river, settling into the lake, new sediment is laid on top of older sediment. So if we're looking at a set of rock strata, the oldest layers are going to be at the bottom and the youngest layers are going to be at the top. That's what you want to think about here as you're putting those samples into the order of relative age dating, with the youngest sample on the top. So what are you going to think about then? Well, in this case, you need to think about the number of unstable Lake Champlainium atoms remaining. So the sample that is going to be the youngest is the one that has many parent isotopes remaining, and the sample that is the oldest is going to have the fewest parent isotopes remaining. So first start by putting them in relative age order. In the next column over, you're going to copy down both the name of the organism and then actually how many unstable parent isotopes they have. And then you're going to be heading into this third column here where you need to figure out how many years ago the organism actually died. So you're going to be transitioning from thinking about relative age dating, which tells you if something is younger or older than something else, to absolute age dating and giving it an exact age. So the way that you're going to do that is actually by working with your graph here. I'm just going to pause and I'm going to make a couple of things disappear and then I'm going to add them back in as we talk. All right, so the first thing that we need to know is that Lillian Gagnon has 80% of the Lake Champlainium atoms remaining. Here we can use our graph as a tool. So remember, our y-axis is percent atoms remaining. We know that she has 80 atoms left. So I'm going to find on the axis of this graph using the scale where 80 would be. So here's 75, here's 100. On this particular graph, each gradation is going up by 5. So 80% would be right here. I would then use my ruler or straight edge in order to draw a neat, clear line that goes from 80 over to the curve of my Lake Champlainium atoms. Again, you do want to do this with a ruler, both so it's readable and legible to you and to others. We're then going to look for where that dotted line that I've shown here intersects with the blue curve, with the Lake Champlainium atoms. And from there, I'm going to turn my ruler vertically, and I'm going to draw, using that straight edge, a line that goes from that intersection point all the way down to my x-axis. And I want to see where it intersects with time in years. So you'll notice that it's intersecting approximately right here. That intersection point is going to tell me the age in time of years for Lillian Gagnon. So notice I've circled 200 here. The other thing that I want to do, because I'm going to be drawing several different lines on this graph, is I'm going to label that line with that sample's name. So this first one here is for Lillian Gagnon. You're going to repeat that same process for each of the 5 other remaining samples, again using a ruler each time, labeling it neatly with that person's name. And once you've done that, you're going to go back to your data table, and in the very final column where it says years ago the organism died, you're going to fill in their absolute age. Once you've done that, of course, you're going to go back and you're going to finish the analysis questions that follow up after that graph. And hopefully you're going to be able to figure out if your relative age dating was a good predictor of the absolute ages. Hopefully that helps, and I look forward to seeing your final product.